Hi everyone, and welcome to today's session. Today we'll be talking about some basics of transformers, ChatGPT, and prompt engineering. And then after that, we'll go through some of like the projects that could be done for like the study group. And this one actually is just like a condensed version of whatever I have so far on YouTube. I just want to make it very brief and concise. If you want to see the longer version, you can go see the full video. All right, so firstly, what is a transformer? All right, this word has taken the world by storm. It started in 2017. Okay, by this paper called Attention is All You Need. Okay, this is what powers the modern ChatGPT, modern large language models. All of them use a variant of the transformer architecture. So before I go into transformers, I think one very important thing for y'all to know is this thing called embedding space. Okay, because this embedding space looks like this. All right, imagine if you were to cluster like concepts together, like these words, you would naturally think that, oh, stuff like cat and kitten, the same stuff should be somewhere nearby in this embedding space, right? Embedding space is like a space with some meaning, all right? And then like non-living objects, like maybe houses, should be far, far away from this area because like this is living and this is non-living. So like a dog is closer to cat and kitten because a dog is also a living creature, okay? But it's not a cat, so it's like away from this cluster here. So wouldn't it be great if we can cluster similar words together so that next time when you want to use it, all right, you can actually reference like what you have learned before. Like next time you have, maybe you in your data set, you have a lot of words like cat, and then like you have like 2 instances of kitten. You can use the meaning learned from cat to evaluate kitten. So it can help to solve a lot of problems of generalization. Because if you have the same kind of words or similar meaning, you can phrase them in different ways. Like, you know, why ChatGPT can do like Chinese translation, although it doesn't really see that much Chinese text or some other language? It's because if you can map stuff into this latent space or this semantic space, which is like the word embedding space, you could potentially do this kind of generalization. Okay, again, this is potentially because it really depends on your data. Because all these embeddings here, you can see over here, this is like an example. In the transformer, we don't actually specify these categories because you can't, okay? It's not that easy to do so, right? But for instance, like you can see living being, like cat is higher and house is lower. So ideally, each of these dimensions should be independent, and then you can learn these different representations so that it can be used for different situations. Okay, so this is more or less the idea. I mean, this is, the bottom part is quite a famous example whereby, you know, if you were to transfer from like man to woman, all right, and king to queen, your embedding vector should be the same direction because it's like going from male to female. So you can reuse this direction. You can, from man to woman, you can start. So there's this very famous thing called like man plus woman minus king equals to queen. You can do this kind of like vector arithmetic if you represent your embedding space well enough. All right, so this is something that also helps with generalization. Okay, so this is more or less the embedding space. Now let's take a look at the transformer architecture. Okay, so I don't want to go through too much of the details here, but there's one quite important thing in the transformer architecture. Okay, and this very important thing is called the attention layer, this multi-head attention. So the original transformer, all right, contains an encoder and a decoder. So the encoder is this part here. All right, and the decoder is this part here. Okay, the reason why we have encoder and decoder, okay, is because last time it used to be like encoder is the text we translate, and the decoder is the text to be translated. So last time when we used to do like recurrent neural networks, encoder decoder was used. So this is like similar for a transformer model. So like, for example, the input here would be something like JS use. Okay, I don't know what French, but you know, like I'm a student. Okay, let's suppose this is the French way. Okay, and then you are supposed to translate this to I am a student. Right. So what this does is, if you look at this encoder, how I view this encoder is this is like the dictionary. This is like the dictionary. Encoder is something like a dictionary. It provides key value pairs. All right. So remember, like, let's say if you want to translate from English to Chinese, like you don't really know how to spell the Chinese words, then you flip to the right page of the English to Chinese dictionary, and then you see, okay, this is like, this word translates to what? Something like that. So this provides key value pairs that can be used such that So this whole thing is something like referencing a dictionary. So in your multi-headed attention, you have the key, the value, and the query. Okay, so now I'm going to talk a little bit more on the attention layer. So the attention layer is there because, you know, in life, we don't really want to pay attention to everything because only some things are important. So this is like give an example. Like for example, you have a particular word that you want to translate, all right, but you don't have that idea of like what word it is. So you need to pay attention to, like, let's say you have a whole list of dictionary words. You need to pay attention to what is relevant for the word. So for example, I have a sentence called I am happy. All right. So if your dictionary has these two words like jubilant, very elated or something, I mean, and then you have another one is like sad, sorrowful. So anyone can tell me, like, if you have a dictionary, you want to translate this. Okay, let's say this is for example, in French, you want to translate this to English. All right. What word would you want to pay attention to in your dictionary? Anyone can tell me which word is more important, like the jubilant or the sad? Which one is more related to happy? All right. So I'll just pause for a while if you want to respond. Okay, so I see some stuff in the chat. Let me just take a look. Yeah, jubilant. Okay, that's good. So what we want to do is we want to map it to somewhere in this dictionary, right? That something is more relevant to it. Okay, and this means that you can take the meaning of this. So this is actually a key value pair, key value. What we can do is we can try to map, like let's say, for example, this sentence, I'm happy, you imagine this as a French sentence, okay? I mean, because like we want to translate this to English. And what we will do is if let's say this is like the French to English translation, this is the French word and then this will be the English word. Or if you are treating as like understanding, this happy can map to something similar, jubilant, and you can get a similar meaning. So this is the query. Whatever you are using to check the meaning is the query. So we want to find out which key matches the query more exactly, and then we pay more weightage to this value here. So instead of just doing a one-to-one dictionary mapping, what the transformer is actually doing is doing this thing called a soft mapping, where you not only map to one, but you can map to different keys. Let's say we have another key here called like happy. Let's say we really have another feeling of joy, or maybe we can have joyful, right? So let's say if we have another joyful here, what we can do is we can do some form of hedging, all right? Instead of just mapping to one key, we can say that, oh, 70% of this I will map to jubilant and maybe 30% to joyful. So what I will do in the end is I will take these two values here, feeling of joy and very elated. I will take these two values and I will average it out in proportion to how much similarity the query is to the key, because this joyful and jubilant are both important. So we can get a combination of values. So this is quite interesting because this mechanism allows us to adapt the initial word embeddings. Okay, like for example, the word happy might be represented in a certain embedding, but once you reference certain dictionaries, like from the encoder, like your decoder, this embedding here, which comes from this output embedding layer, we map the text into this thing called tokens. Like for simplicity, we just treat the tokens as words. So I am a student, okay? So like I will be mapped to a token, and then like we will pay attention to like this part here, and then in the translation we'll see like which is the word we want to pay attention to, and then output will be I. So the first one here will be a blank for the original transformer, and then you're supposed to predict what's the first word, like I, because you pay attention to this word called je. So this is like how we do the French to English translation. We try to pay attention to which of these words here. Every single word here is the key and the value for your dictionary. You pay attention to the dictionary and you see what word you want to output. Then after you output this, you go down here to the input again, and then you try to output the second word, which is M. All right, so you do this process iteratively, and that's roughly how a transformer works. Okay, so I have one last point to talk about this slide before I move on. Okay, and this is the idea of iterative self-attention layers or iterative cross-attention layers like this. So this part here, where we do the iterative attention, iterative attention. This is quite useful, okay, because of this thing called polysemy. All right, so polysemy is something like this. You have this thing called like riverbank, and riverbank has, bank has two meanings. Okay, bank has like something, a financial institution, and bank has another meaning called the riverbank. So how do you know in a sentence what is the meaning of bank, right? And this self-attention could potentially help to solve it. So like, for example, the sentence, Mary went to the river bank. Okay. Initially, bank has a generic embedding space. Like it could be half-half between the financial institution and the river bank, because half of it maybe appears, maybe in the training set, financial institution and river bank, both meanings appear equally. So this bank here is like half-half. Like you don't know whether is it financial institution or you don't know whether is it river bank. This is like the layer one, all right? Layer one, your bank itself is like 50% is finance and then 50% is river. As you go down the next layer, this word bank, okay, can pay attention to the words before it. So you can see that if we do this, what will happen is that river, the meaning of river can go into bank. So like over here, it could be like 90% river and 10% finance. Yeah, so this is like roughly how the attention layer works. When we keep paying attention iteratively, we can update the meaning of the words, okay, from the start all the way to the end. And then at the end, when we finally predict the next token, it will be like the most representative meaning of that word or that token. All right. So yeah, I think that's more or less what I wanted to cover. The math, I leave it to you to figure it out, okay, because I just want to get the concept across. There's this also other thing called positional encoding, okay, which is needed because in English words or in like sequences of text, you do not want the words to not have any meaning of sequence. Okay, let me give you an example. All right, the one example is like that. If we have this word called like John hit Mary, all right, versus Mary hit John. Can y'all see that the context is different? So we kind of want to preserve the position, and we do so by a positional embedding. We add in a certain sinusoidal wave to the embedding space, and this sinusoidal wave, okay, the words that are closer together, if you do a cosine, okay, you do a cosine of the two embeddings, embedding one, embedding two, or pos one, pos two, it will be smaller than the okay, so if you do the embedding, sorry, I think this will be, cosine similarity will be higher, yeah, will be greater. So the closer words, okay, would have a higher similarity compared to like words that are further away. Like this. Yeah, I can't remember the equation here, but let me just go and verify this. But the idea is the closer words, you will pay more attention to them. Okay, and the further away the words are, you'll pay less attention to those words. So there's some form of like a soft window that you can pay attention to. Like if you have a very long text, like John hit Mary, and then you have lorem ipsum, and so on. You have a very, very long text. You may only pay attention, like John may only pay attention to these three words. And then like, for example, sorry, hit will pay attention to these three words, and like maybe Lorem will pay attention to these three words, because you only pay attention to your neighbors more due to this positional embeddings. And that's the purpose of it. Okay, to me, I think this is like a very funny hack because it is not very natural to the architecture to just put in this. Okay, I mean, if you have studied RNNs before, RNNs work like that. You have one RNN cell. Okay, you have your input going to the RNN cell, and then you have your hidden layer. So this is more natural, like your position will be encoded because your words go in one by one. So this is an RNN, recurrent neural network. And like here you have like stuff like John, Tip, Mary. Yeah, so this is more natural for recurrent networks where you have this position already embedded in the architecture. But unfortunately for transformers, we kind of lose out on this recursive part. Okay, so we have to put in some positional encoding. If not, when you switch the order of the tokens, it doesn't really work. Okay, so I hope this is clear why this is the case. Yeah, I mean, since I already drew this diagram, I also like to emphasize that the reason why transformers also work much better than this kind of like recurrent architectures is because like this is actually the hidden layer here, the hidden vector or hidden embedding, that you actually have only one hidden vector passing through here. So, you know, it's like when you go through an expressway, suddenly you filter out to a small lane. You know, all the information needs to go through that lane. So you might lose quite a lot of information because of that. I mean, structures like the long short-term transformer, long short-term memory, you have two of them. You have you have two hidden vectors that go through. Okay, but still there's also a bottleneck. Transformers, on the other hand, if you see in the architectures later, you will see that all these things will go straight through. You will go through all of this information of all your tokens, okay, all the way until the end, right? So there's actually not much info leakage. So there's you solve a bit of this information bottleneck problem. Okay, so that's also one of the reasons why transformers work better. Okay, so before I move on, anyone want to ask any clarifications on this? I covered quite a bit of concepts here, but I thought this one will be quite useful. Okay, so I think I have to hurry a bit. So I will skip all this, okay, because I don't have time to go through. But the main thing I want to talk about is what I covered here, which is basically like you have a query, you match the keys that are similar. So for example, thinking machines, okay, you match, okay, thinking will match to itself higher than thinking will go to machines. So this is the idea. And then once we do that, okay, when we update the embedding space, okay, if let's say thinking itself is a higher weightage, okay, when we go through the softmax, okay, we will regulate like 88% of the value will come from thinking and 12% will come from machines. All right, and in the end, what we do is we'll do a weighted sum of the values. So for example, when we update the value here, this updated value here, okay, will be 0.88 of this and 0.12 of this. So we update the representational space here, the embedding space. We update the representational space of thinking, okay, by updating it mainly by the previous value or the same value as above, this value. But we also give some context from machines. Okay, so like this thinking itself will be an amalgamation of both the meaning of thinking and machines, but more towards thinking because thinking is more relevant to thinking than machines is to thinking. Okay, so this is more or less how attention works. Okay, so this is like how the attention layers work. Like for example, the word it or the token it can attend to all this. Okay, then you can attend to, like for example, tired. You attend to it more in one attention head, but there can also be another attention head. Okay, because like when we attend to words, you need not only just use one layer to attend to it. You can use parallel layers so that, like for example, it attend to tired is like maybe talking about feelings, adjectives. Yeah. Then it can also attend to this. The animal didn't. So this one will be more of like maybe syntax. It goes to the animal. All right. So this is like pronouns or something. So one layer can attend to pronouns. So like you have multi-head attention. Okay. Each head can attend to a different attribute. Okay, but now I tell you, okay, this one is for pronouns, this one is for tired. You know, actually, if you go and look at the transformer architecture and you look at the weights, right? You can't really tell much. You have to infer from some human insight what is it attending to, because you know, humans, we don't actually program in, oh, you are a pronoun looker, you are a grammar looker. The way this is learned is through backpropagation from the reward signal or the error signal, and these are just learned by the model themselves from the data. So this is our best guess at what this layer is doing, but most times actually we don't know what the layer is doing. Okay, just to let you know. All right, so now we go to GPT. Just now I was talking about the transformer architecture. So GPT, what it does is that it takes away the entire encoder block. It just does a decoder block. Then you must be wondering, where's the dictionary that it references from, right? So it just references the context. So this first part here is your dictionary. So like when you do ChatGPT, you say that you are a sales assistant. Okay, then reply to this message. you are actually conditioning on this as your context. So these tokens will come first. And then when you generate this message, all this stuff at the front, okay, will be used to generate the next token one by one. So this is why we can do prompt engineering, right? Because we can actually ground the earlier stuff with some context, and then we can keep generating stuff next again and again and again. All right, this is also possible because instead of doing self-attention on all the tokens like in the original models for transformer, all right, we are only doing mass self-attention, which is like for a given token, okay, you only pay attention to the words before it, okay, because this self-attention is like stuff like birds, okay, birds pays attention to both the backwards and the forward part because it's bidirectional. So what they did in the training is that they actually mask out certain tokens randomly, about 15% of their tokens, and they try to predict all these tokens. All right, so this is actually a good way to like reuse data because like one single sentence can have multiple ways of like masking, and they predict the mask. However, it's not very natural for text generation because for text generation, you kind of don't have the future text. You kind of only can generate text from like where you are, you just generate from that point onwards. Okay, like for example, you are sales assistant, reply to this message X, right? You don't have like, this is your generated content, then ending message. You kind of don't have this format when you like drafting letters and so on. You don't have the ending message and then you like fill in the middle, right? Normally what you do is you take out the instructions at the start and then you generate all the way at the back. So GPT, this decoder-only architecture, is more natural for those kind of instruction-based tasks where you have some instruction at the beginning, then you want to generate the response for that task, right? So one good thing about only having the decoder block, all right, is that there's fewer ways to learn. So what GPT managed to do is they managed to massively increase this one. So they did over 100 GB, 100 I think 100 billion weights in this part here. So GPT is huge, all right? It's massive. And they massively increase the size of each decoder block. They increase the number of layers. And somehow from this increase in scale, as well as increase in the amount of data they use, GPT is quite powerful. Yeah, I mean, if you have used ChatGPT, it can answer quite a lot of questions and it's very like general. So apparently increasing this scale of the decoder block is enough. You don't even need the encoder block. All right. All right, so there's a question. I thought the encoder creates a deeper representation of the inputs. How come this deeper representation doesn't seem useful for instruction-tuned models? Okay, so for the encoder, if you have like some useful stuff to like condition on, like for example, if you want to talk about memory, about like maybe like if you are doing some question answer, you could maybe in your encoder reference the document. Then your decoder could reference that document as the key value pairs, because remember for the encoder decoder block, the encoder supplies the key value pairs. Oops. And the decoder is the query. So the thing is, yes, it might help better with the like memory referencing because you offload the referencing to the self-attention step here. You don't really need to do self-attention on the decoder block. You don't have to do the self-attention means the key value and query come all from this decoder block. So that's self-attention. So right now GPT is doing self-attention. Okay, if you split in the encoder, maybe the benefit is that you can offload like your tokens in the encoder. You don't have to feed it in. Yeah. I think one of the main reasons why they didn't want to continue with the encoder decoder architecture was that there was no need to. Like people have found that if you just put your like documents here at the start, it works about the same. Yeah, I don't know if you have experience with the encoder decoder model, you can see whether or not is it better than GPT. Yeah, but based on like my experience, GPT, maybe because of their size, works much better than the encoder decoder models. Yeah, and it's also easier to train actually if you don't have the encoder block because fewer weights. You can just concentrate your efforts only on this decoder side. Yeah, I hope that answered the question. Yeah, decoder is easier to train, much easier. Yeah, you don't have. All right, so let's go about over the training of transformers. So normally what transformers do is we have two phases. One is the unsupervised pre-training, where basically you take in the internet data, okay, and then you take the sentence and then you just cut off halfway, and then you just mask the next token, and then you also predict cat. And then the cat is that you need to predict the next word, which is like on. And then the cat is on then you predict mat. So what's the benefit of this? This unsupervised pre-training or self-supervised pre-training can be done without human labels. Okay, you know, there's this trend in machine learning last time with AlexNet. Supervised learning came about where you do supervised learning on images. However, we have shown that this actually doesn't scale up very well because like more than 90% of the internet's data are unlabeled. Right? You want to do sentiment analysis, you want to say this is happy, sad. You know, there's so few data that is labeled. Yeah, IMDb movie data set. I mean, how much effort do you need to label everything? Okay, but if you can do a training that doesn't require human labels, you essentially can use the whole internet's data. And that's what GPT is doing. They use the entire internet's data by doing this next token prediction. Okay, and it turns out that this next token prediction, okay, can actually learn the structure quite well. Learns the structure of the text. Okay, so this is also one of the problems with GPT training, all right? Right now, the internet text is by humans, all right? If next time when we have AI creating the text, your structure will be following the AI structure. So, you know, there's only so much you can learn if, let's say, humans don't create the text anymore. After a while, it'll be AI learning on itself. So you start to wonder whether GPT's performance can continue to increase because they more or less use up the entire internet already. So that's just a side point. But the idea is we can learn the text structure quite well. Like if, for example, you have structures such as like A is the father of B, and like C is the daughter of A, something like that. Yeah, you can actually like ask it to say like A is the or B is the, then you can like sort of predict son of A. B is the son of, then you ask it to predict this. Yeah, so this actually kind of learns like relational relationships, because even though you're just doing next token prediction, in order to do this next token prediction correctly, you need to not only know like the rough probabilities of the next token, you need to sort of understand at a higher level, this is a structure, okay, this is a sentence, and this whole thing is a paragraph, and then this paragraph contains this information which you need to pay attention to in order to predict this one here. So after a while, you will learn higher level structure, higher level paragraphing and everything, which is quite what you observe in ChatGPT. Like its paragraphs are structured pretty well. Yeah, it seems that if you scale up the model, you can actually learn higher level relationships more than just like one token predict the next. You learn like one sentence, this next part, what do you predict? You can enable stuff like prompt engineering, where you can have the whole text at the start as the prompt, and then you do the next prediction like that. Yeah, so this is quite amazing. And this next token prediction is very powerful. All right, so this is unsupervised pre-training. The other part is called fine-tuning. And fine-tuning is basically you have a sequence of tokens, okay, to match your response. So this is actually called training on your data. All right. I think GPT is coming out soon. ChatGPT is going to release an API where you can do this fine-tuning step yourself. So this is the training on your data part. And I think this is quite useful next time if you have your own specific use case. All right, so there's this thing called one prompt equals to 1,000 examples. I can't remember who wrote that paper, but basically they said that like if you prompt engineer it, it's equivalent to like fine-tuning on 1,000 examples. So the thing is, if you have very, very specific use case, sometimes you cannot just prompt engineer. Like I'm trying to solve the ARC challenge, abstraction and reasoning corpus challenge with prompt engineering, basically, with LLMs as a system. I realized that like the context limit is quite easily hit. Okay, I mean, y'all probably don't realize it, but because I have quite specific stuff I want to tune the model to, the 8,000 token limit hits very easily. Yeah, so for cases like this, maybe fine-tuning would be better. Then you don't have to have a very lengthy top part to do this prompting. And it helps you save tokens as well. The downside is, you know, GPT updates their models quite regularly. The moment they update their model one time, your fine-tuning is gone. All right, you have to fine tune on a new model, unless you are okay with the old model. All right, so this is the fine tuning step where we train on the data. Okay, in the modern ChatGPT, this is called there's also this like supervised fine tuning step. And then after that, you have reinforcement learning from human feedback. Okay, due to the short time, I'm not going to cover this RLHF part. Okay, but it's been shown that RLHF actually not very needed. Okay, if you actually have good fine-tuning data. So you can check this paper, Lima, less is more for alignment. Okay, they showed that like if they take away the RLHF step, but you do very good fine-tuning on your data, it works probably just as well as RLHF. You don't really need RLHF. So this fine-tuning part, good if you want to do on your data and you don't want to prompt engineer that much. Okay, but this part here, this unsupervised pre-training, is very, very important because this is where GPT gets all its general capabilities from. Okay, it's able to do a lot of different tasks. Because if you have that kind of task on the web, like you have code on the web, you have like story writing on the web, you have like customer queries on the web, you can actually learn from all this data. And the best part of it is that one domain can actually transfer to another if, let's say, they use the same kind of structure. So yeah, I think this is something that I like a lot about the transformer model because it allows for next token prediction. This part here, I like this part a lot. Okay, Yen LeCun likes this part also, self-supervised learning. Yeah, I really think this is like the basis of intelligence, trying to do prediction and from prediction to learn structure. Okay, I think I spent a lot of time on this. I'm so sorry. I think I will overshoot the time a bit. So let's just go to the next part. So this part is on next token loss. So for next token loss, what we do is we are just trying to predict like the next token, and we are trying to maximize the likelihood of the prediction of the next token. And then from that loss function, okay, we just backpropagate and we update the weights of the neural network. Okay, let's move on. All right, so this is the idea. So like, for example, you have thinking machines. The next token is R, 80%. So if you set your temperature in GPT, temperature to be 0, then you will just do a greedy selection, which means that you will always select R. Okay, but if you set your temperature to be higher, you will select more randomly. All right. So this is the idea of temperature, but let's say for now we use like greedy selection. So like for the token probabilities, we have R, and then after that we feed in this again, and then you get the next one useful. So I don't know if you all have seen this, but the longer your output text, the longer it takes to generate. Okay, that's because GPT is generating token by token. Okay, so this means that if you have a token length of 1,000, you need to generate this process 1,000 times. You need to feed these tokens through this model 1,000 times. Okay, because each time you only generate one token. So you keep doing this. After you generate this token, you feed this token at the start, and then you generate your next token again. So this process, you just repeat and repeat again. Yeah. Okay, I have a question now. For your father and son relationship example, does ChatGPT recognize the predicted token without use of embedding? I think it does. Yeah. So, okay, but what do you mean without the use of an embedding? Because it actually outputs in embedding space. Like this part here is still in embedding space. This add and normalize layer. This is still the embedding space. Yeah, so I'm not too sure what you mean by without the use of an embedding. Yeah, it still uses embedding. And then after that, it just converts them into a probability layer using softmax. Yeah, the embedding is all the way throughout. They use, transformers use the same embedding representation, like 1024 hidden units from all the way from the beginning to the end. So like, again, sorry, not all the way from the beginning. I think for this part here, maybe 764 units for the, and then after that, the middle part is 1024 units. If I remember correctly, like, I mean, you can mix and match this architecture, but the idea is the hidden units are always the same in this part here.
Thanks, John. I figure that it's easy if I speak on microphone.
Okay, sure.
Yeah, so my question is, right, I was thinking about the embedding part because, I was thinking about how they actually predict the tokens, by having to figure out the father and son relationship. So there has to be embedding somewhere. So is it a case whereby, you know, when we enter more prompts, the embedding space actually increases as well?
Yeah. The embedding space doesn't increase. Embedding space is like the latent representation of your token. So like it's always fixed. It's the same units. Like you have, like if we go back to the earlier slide, the embedding space is this one. This part here, like you try to represent different different entities in each of these columns, and each of these columns like represent maybe a different attribute. So like for each token, the embedding space is the same length. Like
Okay, so no matter,
yeah.
I see. So no matter what, it's already pre-trained to contain a certain number of tokens, it doesn't increases as we type in more complex
Yes, correct.
numbers.
What increases is maybe the accuracy of your embedding. Like if you train more, cat and kitten will go together. You know, initially maybe the kitten is here, but as you train, the embedding will get closer and closer to each other.
And does that is that due to more prompts, or
It's
is
nothing to
it
do with the prompts. It's just based on like statistical significance. Like for example, if let's say I say the cat played with this, and then maybe like the kitten played with the ball. You know, if this kind of appears like many times, you know, after a while you learn that cat and kitten are about the same.
okay? Yeah, thanks so much.
So this is actually the key thing that drives generalization. You know, why do you think you can prompt engineer to a new situation? It's because your words or your tokens are already trained. And these tokens, if you mix and match the meaning through self-attention, you can get a new context. You know, like mixing and matching is actually very powerful. And this mixing and matching is exactly what self-attention is doing. Yeah, GPT is a great associator. And you know, if you think association can create intelligence, then GPT is intelligent. I think GPT is the fundamentals of an intelligent system. Yeah, this will be more or less powering AGI in the future, this kind of system. It may not be the transformer in the middle, but this kind of next token generation, because you do the next token prediction objective, I think this will power intelligence. At least that's my view. Okay, I think I exceeded a bit. Now is like close to the end. I will probably like not go through the prompt engineering that much. We go through the applications more. Okay, but first let me answer some questions that you all have. Can we prompt engineer to fool the embedding? For example, in the embedding cat is very related to kitten. Is there a way to fool the transformer to think they are not related using prompt engineering? Of course, you know, it's been shown that if you go like use a different meaning of words, like for example, like rank the following, or like give the following classifications. So like, I am happy, you classify as sad. I am sad, you classify as happy. So you know, it's been shown that if you do something like that, like you give the reverse meaning of it, like you might actually fool the system to like think that, oh, sad is happy, you know, happy, sad, you know, that kind of stuff. You can actually do that. But one thing is that the larger the model, the less susceptible, because it's able to see the pattern, and then it can more or less try to decouple this set from the meaning. So this sad and happy, it could see it as like category. So maybe like after this arrow here, it sees this as category instead. So it can decouple like the semantic meaning from it. Yeah, but smaller models, it can fall for it. And I think if you do away with like, or rather if you do RLHF, I think this might be more susceptible to fooling the model like that. I can't remember the exact quotation, so don't quote me on that. But the idea is you can still fool the language model if you give like a different semantic meaning from what the embedding has been trained on. Yeah. So another question, can the embedding layer be kept fixed? Are there many embedding layer as a byproduct of many training, or what do we keep fixed or train with the attention model? Okay, so this is a good question. The embedding model is always fixed. Okay, so if you look over here, the embedding model is like that. You see this input embedding and this output embedding. With the train model, you don't actually train any of this. Okay, what happens is that, let's say you have a vector like cat, it goes to this embedding. It goes to this, and then like dog maybe goes to something like that. Very similar, but not exactly the same. So you might be asking me, just now I said self-attention can solve polysemy. How? I mean, these output embeddings are always going to be the same. The same token goes in, it will just map to the embedding, and then this embedding will be fed into this part here. Then you must be asking me like, how is this possible? Like, why can we get different kind of like mix and match if our input embedding is the same, right? And actually the answer is because of self-attention. Right? Remember just now we can pay attention to different words. So if let's say cat appears closer to like maybe I don't know, humans, then you might actually get some of the embedding values of humans mixed together with cat. Then it will have a different meaning at the end as compared to cats and dogs. Then you have the dog and the cat. The cat might take in some of the meanings of the embedding space of the dog. Right? Some of the values might be like crossed over to the cat. So something like this is what can cause you to create a new context, and then GPT can do this kind of self-attention in order to try to figure out what this new context is. Yeah. So another question: will you think word meaning is controlled by embedding, but language structure and knowledge is controlled by the attention model? No. I mean, the initial word meaning is by embedding, but the final word meaning will still be by attention. What the structure and the knowledge, right, is to learn these embeddings. Yeah. Inherently in this thing here, there's no like sentence layer and like word layer, but normally what you do is like when you first pay attention, you pay attention to the word layer. At the top, you pay attention to the sentence layer. Maybe at the very top, you pay attention to the paragraph. Yeah. So this is by nature of how we do self-attention. Like we kind of like can pay attention to further and further away tokens, because when they mix their values together, you can theoretically form a path that from here attend all the way from the starting to the ending. Yeah. So this is by nature of the iteration. Yeah. So yeah, the whole structure and knowledge thing is all by self-attention. Yeah. But also the word embeddings is also controlled by self-attention, because the word embedding here will be different from the word embedding here most of the time, because you will update the word embedding or the token embedding by by basically what has appeared before it. So the tokens will be updated. Yeah. So yeah, the embedding layer. Okay, I think there's a big. The embedding layer for the output embedding here is fixed, but the embedding is flexible in the sense that through self-attention you can change the embeddings. So as you go through the transformer model from self-attention, you change the embeddings. Okay, do take note, GPT doesn't have encoder, so you can cancel out this part. All good? Okay, I think I probably have to stop here soon. Okay, let me just go through a few interesting slides, because I want to actually go through some of the demo. So this like I think this is quite important. Like, what is a large language model compared to a computer program? Computer program is very, very rigid. Like you have a certain set of rules, but you can replicate the performance. Okay, but GPT is able to do a lot of things through just zero shot and few shot prompting. I will cover zero shot and few shot because I think it's important. It can do intent processing, very important. Intent processing is very important because you can ask GPT to do anything. Okay, so for programs you can't really do it. Okay, it's not very flexible. Okay, but the good thing is if you have computer programs, okay, it's free most of the time. So sometimes what I do is I ask GPT to generate the computer program, then I just keep using the computer program. So that's what I do most of the time. Okay, GPT needs money. Okay, and also take some time to infer if it's very like long. A long output will need a longer time to generate due to the recursion that I've shown you. You need to take the token, bring to the input, and continue. Okay, but it's very, very flexible. Okay, so I believe a good mix will be half-half. Like you use GPT for what it's good at, for creative generation. Use programs for what it's good at, for remembering stuff, for being very exact. Like your memory stuff, you can use a computer program to store the memory. You don't use GPT to store it, okay? But you can give the memory of this program to GPT as context, right? So you can also do stuff like fixed rule-based processing. Like if you have a game, you want to do the game logic, like player 1's turn, player 2's turn. That one can be done by the computer program. But if the game involves some like creative generation of text, that can be done by GPT, all right? So you use each one for their own good stuff. Right, so I think for your projects, do explore this. I think a mixture of both GPT and programming, computer programs is actually the best way ahead. Okay, because GPT is not good at everything. Okay, you will still need some form of reliability and consistency that you can get from a computer program for some use cases. All right, so the key benefits of large language models: very flexible, can perform most tasks without pre-training or programming. Right, and I would like to say that I really love prompt engineering because it got me to do a lot of things. Okay, so this next thing is LLMs can be used not just by itself, but as a system. So you can interface it with plugins, with tools. You can interface it with other LLM programs. Okay, I'm not going to cover too much here. If you're interested, you can watch my other videos on it. So I'm going to skip this as well. This is a baby AGI, or like very similar is AutoGPT. Okay, it's using GPT to break down into subtasks and then like prioritize the task, execute the task. Okay, zero-shot prompting. Okay, this is very important. If you have a use case that is very, okay, so how do I do what to use for prompting? If you can find your data easily available on the web, chances are you can zero-shot it. You can say, I want to generate an essay on the topic large language models. Many essays online. You don't need to give an example. So zero-shot is enough. Okay, so for example, stuff like this: mountain, classroom, garden. GPT has seen it many, many times. Then you can ask it to classify what are these sentences like that. You can ask it to classify all at the same time as well. So later I will be introducing my strict JSON framework, roughly lah. So this can do it like natively in the framework, right? Few shot prompting. So if let's say you really don't have this example online, you can prompt it with some examples. Okay, you can say that you are a certain thing, you are an intent. This is the example of classification like that. Okay, ask it the classification of like the number 6. So this is what could be done as well. And this is useful if your example or if your use case, the content is not commonly found online. All right, so if you should try zero-shot prompting first. If zero-shot fails, use few shot. Okay, that's my advice. Okay, this is the intent framework, like you are what purpose in life. Give the examples and then I give your input. Okay, but more importantly, like this is like the system input will be the purpose in life. And the user input will be like the examples. I mean, you can even put the examples in the system input as well. Examples. User input will be like the specific input case. So in GPT, the API, you have a system and you have a user. This is my recommended framework. You give your intent in your system input. Everything that is like the same kind of generation needed for any input, you give the system message there, like how to behave, what are some examples. Then the user input is just like this part here. Yeah. So yeah, this is more or less how we use the API effectively. All right, so if let's say GPT outputs too much nonsense, how can you control it? So one way to do it is to use a JSON framework, because JSON is widely available. Again, you see JSON is used because JSON is used for most web pages. So when you use a JSON format, GPT immediately knows what it is. All right, so JSON framework is quite a good way to contain the amount of nonsense that GPT is outputting. All right, it becomes much less verbose if you use a JSON framework. So I'm going to introduce my fixed JSON framework roughly. The idea is that you can put in like what intent you want. Okay, you can put in your user prompt, and then you can output like what you want in JSON format, and then it will kind of match like, oh, the sentiment is positive, the tense is present. So I did it because I didn't like LangChain's prompt template way. It's a bit convoluted. Here you just put in your format, your header and your description of it, and out comes the output. And it will even do the error checking. If the output format is not of this format, it will give an error message to GPT, and then through iterative generation, it will ask GPT to correct its mistakes. Yeah, so this is something that I created like last week. I use this quite a lot for my projects. So if you want to use this for your projects in this generative AI study group, you can do it as well. Right now, I don't have it as an API or as a package yet. You just download my notebook from here, copy and paste the strict output function, and you can use it. Okay. So this is more or less it. All right. So what are the projects that y'all can do? Okay. Before I move on, any questions on prompt engineering before I go to showcase some projects? Okay. So for the projects, what we can do is we can do this. Like, I think retrieval augmented generation is very, very useful. And retrieval augmented generation, I didn't cover earlier, but what it does is that you can retrieve relevant memories, like for example, or you retrieve relevant contexts. So you can prompt the model with like maybe top 3 contexts here, and then like answer this question or like answer this question. Who is John? Yeah. So if you don't give it the context, sometimes the question you ask need not actually have like some general meaning. You actually is based on some documents you want to do question answer. Yeah. So this context is quite important. You use top K neighbors usually is relevant to the context. And then you retrieve by cosine similarity. So usually what we can do is we can use OpenAI embeddings to convert a sentence to an embedding space. Right? So this is what you normally do. And then you use a vector database such as Pinecone to store the embedding, store the text plus embeddings. Yeah. So this is like one thing that I think is very useful. Like this retrieval augmented generation will be very, very useful for a lot of applications because you can basically condition GPT on your use case. Okay. Another note, the more specific you are with your prompting with GPT, the better the output. So the more you condition earlier on, the output will be more and more related to your use case. So there's also stuff to do prompt engineering, like we do the broad plan, then the specific plan, and then like your GPT will generate better for the specific plan if you ask it to generate the broad plan before that. Because that's why I said earlier, the tokens that we generate earlier will be used for the generation of the later part. So when we do the specific plan, it will condition everything on whatever you generate for the broad plan. Okay, this is very useful. I use it for everything that I use GPT for. Okay, so this is one example of what we can do for chatbot. Eventually, after you get your chatbot ready, you can use software like Gradio to make it a UI. Yeah, so I mean, these are some examples of what you can do for this. I mean, you can also make it a web browser. Yeah, if you know how to do like HTML uploading, yeah, you can actually do this retrieval augmented generation on the browser. So yeah, some ideas for what you can do for projects. You can use make this game. Later, I'm going to showcase the evolution game with this GPT API. You can also do a website crawler. All right. So now what I'm going to do is I'm going to show you the project basically some of the things that I've created, so you can see like what you want to do. So I'm just going to share my desktop. Yeah, I think I should share my Google Chrome. Hang on for a while. Give me a while. Okay, so I'm going to share with you this one. So, okay, before I share with you this, the strict JSON framework, right? You can just download on the GitHub. The link is there. And what you need to do is you just need to copy and paste this define strict output thing here. This whole function, you copy and paste in your notebook. Then you can use the function already. I mean, the rest of the things I won't go through because it's quite late already. It's basically like saying like what you want, and then you can ask it to generate what you want. You can ask it to generate lists and so on. You can even do something like, out of these 2 categories, generate one of the categories. Okay. You can even do stuff like generate out of this 3, you generate the label A, B, or C. Then I also make it very funky. You can also do something like this. You can do this angle brackets to say that, oh, GPT will dynamically come up with this description itself, right? And you can do chain of thought prompting, like the broad and specific like that, using the JSON. You can even do like React framework using JSON. The action, thoughts, actions, observations, you can do that. All right. I mean, the rest, I leave it to you to explore, right? I'm not going to cover this. Okay, the other thing is like this evolution game. I think I demoed it the last time with text only, but now we can actually do like, this is the user prompt. All right. Sorry, this is the system prompt to say like, what's the game about? The user prompt is like the memory of what happened before, what did the player choose, and the current phase. And then like the output format will be like describing this phase. And then what we can do is we can also interface this with like the DALL-E framework, the DALL-E API to display images. Like over here, I ask it to, based on the options, okay, create 3 images using the DALL-E API. Okay, that reflects the option description here. So you can see, like, for example, you are a protozoa and a pawn. You have the 3 attributes: photosynthetic, motile, and filter feeder. So this first one is photosynthetic, second one is motile, and the third one is filter feeder. So we can just pick one, like maybe I pick motile. And then GPT will go to the next phase, which is, and the phase here you can see, I actually use, sorry, I didn't, yeah. I did, yeah. I use a rule-based phase thing so that like it knows that goes to the next phase is here, find a creature. Yeah, so this is an example of what I said earlier. You can mix rule-based with ChatGPT style flexibility. So, right, so we have moved to the next one. Like you can choose to find a creature. One is amoeba, second is paramecium, and third is euglena. So you see this goes to the DALL-E interface, and then you can get the images out. Okay, the only downside is that if you don't have your own image generation and use the DALL-E API, one image is 2 cents. So right now this is 6 cents generated. So yeah, I guess if you have a lot of money, this is fine. But yeah, definitely there should be cheaper options next time. Okay, the last one I won't go through in detail. I'll probably create a video on it shortly. This is basically what I did to like search through the web to query like large language model courses or what. I want it to be in this format. Okay, and then I will basically like use a web browsing tool. Okay, I'll skip all this. And what I'll do is I will ask GPT to come up with 3 ways to prompt Google. All right, these are the 3 search terms. Then I will go through the Google API and get the website list. Through the website list, I get the main URL and the sub URLs, okay, that are relevant for the search query. Okay, after that, what I do is I will have this curated list here. And because I don't want to search all these things from one site itself, I ask GPT to say that, okay, find the max URLs relevant for the query. So like for every site, the primary and the secondary links, I only curate down to 3, 1, 2, 3. I mean, up to you how many you want. Then after this, what I do is I will just go through all the created lists one by one, and then I'll ask it to fill up the different fields. Then I'll ask GPT again using the strict output format to say that, okay, ask them to combine if there's any overlap of any fields, and then ask it to rank by relevance. Okay, so you can see that I used basically the strict output function for practically everything here. And I think this is like way better than LangChain, in my opinion. So yeah, this is the final, like, this is the course description and the website of like 10, I just used 10 different links to generate this list. So this is a WebScraper created using GPT and Selenium for web browsing. So yeah, I think I'll end here. Any questions so far on the projects? Yeah, I'm gonna basically stop recording, then we'll have a free flow session after this. Okay, let's see. Does the GPT API have access to plugins? No, unfortunately not at the moment. Yeah, I couldn't use the web browsing plugin from GPT. Anyway, they recently took it down because I think there's some copyright issues. Yeah, so I think this is like the closest you can get to web browsing. You can use GPT, and then like you can basically ask the like there's this way to load the website. Let me just show you. Yeah, you can actually get the like here, view URL. I created this function. You can actually use like this Selenium to pass the website. Yeah, so this is what I did. By the way, I'm not an expert in website scraping. I basically created this using GPT. I just asked GPT, hi, I would like to create a web scraper. What code can I use? Then I just copy paste the code, put their error message, copy paste back. Then basically I created this whole thing without any experience of web scraping. Yeah, so this is the power of ChatGPT. So yeah, same thing for this evolution game. I didn't know how to use this, what do you call that? Yeah, this DALL-E API. Yeah, okay, this one I didn't use GPT because like more recent stuff it cannot do. I actually went to the OpenAI site and copy and paste. Yeah, so there's a lot of things that you can do that is quite intuitive. You just need to search. Okay, so don't let inexperience hinder you from doing it, because I can tell you I don't know how to do web scraping. I don't know how to do image generation API. I managed to do it. Yeah, so it's all about a matter of like using GPT to search or using the web to search. Okay, I'm going to stop recording now, and then we can start talking anything. All right.